So 2 more induction proofs for us, and then I'll have a third one that I'm going to ask you to be practicing on your own. What to pay attention to in these, again, first of all, is the overall structure remains the same. Right? If we're going to prove a statement quantified on the natural numbers by induction, we're going to take a base case, which shows that the first domino in the infinite line of dominoes can be toppled over. And then we'll take an inductive hypothesis that says, let's assume that the kth, arbitrary kth case is true, that that domino falls. And then we have to demonstrate that that makes the next domino topple over. So that overall structure remains the same. The only thing that's going to be different about these examples is that the particulars of the statements we're proving are going to involve some inequalities, which inequality work is super important for later on, especially when you do courses like Introduction to Analysis. And then also a proof using divisibility, which is more useful in the sort of the discrete math, combinatorics, number theory side of the mathematical discipline. So this gives a couple of good illustrations about how proof by induction is useful sort of across the whole mathematical enterprise by exploring these couple of cases. So the first one I want to look at is this one. We're going to prove an inequality that for all n greater than or equal to 6, that this inequality, 10n squared plus 3n plus 3, is greater than or equal to 60n plus 20, is true. This feels like a very technical statement, right? But where this kind of thing shows up is, for example, even in second semester calculus. So in second semester calculus, one of the things that we end up doing a lot is trying to take infinite series of real numbers. So I'm trying to add up an infinite collection of real numbers. And if I want to know whether that infinite sum actually adds up to something finite, one of the things I can do is to try to compare the terms in that sum to the terms in another sum, which I already know whether or not it adds up to something finite. Right? It's called the comparison test, or the direct comparison test. If you're taking Calc 2 now, or if you've taken Calc 2 before, or taken AP Calculus in high school, that might ring a bell, the direct comparison test. And these are the kinds of inequalities that we could use to explore a direct comparison. For example, if I already know that, if I add up all of the 60n plus 20s, so if n starts from 6, this would be 36,080 plus 30, I don't know. So it's got a bunch of natural numbers. If I add those all up, and if they add up to infinity, and I know that all of these are greater than or equal to those, then if I'm adding these up, I'm going to be adding a bunch of numbers which are greater than the sum of a bunch of numbers which add up to infinity, and therefore the sum of these numbers must also add up to infinity. It's the kind of direct comparison that we do. And so this is the kind of proof that could be used to really sort of firm foundation show why this comparison that we're trying to make is actually a valid comparison for n's greater than or equal to 6. So let's establish this inequality. And as I did in our last class, I want to start these proofs so that we can focus the most attention on the inductive steps. And we'll do the base cases as sort of afterthoughts, remembering that both of those need to be included in a polished proof. So for the inductive step, we have an inductive hypothesis to take. We're going to assume that this inequality is satisfied for some arbitrary k greater than or equal to 6. All right, so assume 10k squared plus 3k plus 3 is greater than or equal to 60k plus 20. And from that assumption, we want to be able to deduce the statement for k plus 1. So 10 times the quantity k plus 1 squared plus 3 times the quantity k plus 1 plus 3. We need to show that that's greater than or equal to 60 times the quantity k plus 1 plus 20. So this is a place where on your napkin you might do some work on both sides of the inequality. On my napkin, I like to give myself a bunch of room and try to get from one side to the other. Again, well, as long as you're still on your scratch paper, this is your playground to manipulate this inequality in whatever way is going to illustrate for you how it follows from the inductive hypothesis written in blue. And as usual, our burden of proof here is going to be to figure out how to connect this expression, which we don't know anything about the value of. How do we connect it back to, let's say, this expression, which we do know something about? We don't exactly know what its value is, but we have what analysts call an estimate for it. We know that it's greater than or equal to some other quantity, right? So it can't just be any old thing. We know it has to be greater than or equal to this other thing, right? And as usual, for these kinds of problems, algebra is the key. So we'll just try to expand out these parentheses here so that we can try to discover these three terms within this expression. So we can also, again, this is me doing a little bit of both sides work here. We can also eliminate the parentheses from this right-hand side expression just by distributing the 60 across the k plus 1. So I end up getting 60k plus 60 plus 80. It's going to give me 60k plus 60 plus 20, rather. So 60k plus 80. Okay, so we'll expand out that left-hand side. 10k squared plus 20k plus 10, that's what I get from this first term here, and then 3k plus 3 plus 3. And I'm actually going to leave this algebra unsimplified. Rather than trying to get all the like terms together too quickly, this is a good place to pause and say, can I find the pieces that I'm trying to find for my inductive hypothesis within this expression? And it turns out that I can, right? I can find a 10k squared term right there. I can find a 3k term sitting right over here, and I can find a plus 3 sitting right there. Right? So I might have lost out on that intuition if I had been too quick to combine my like terms. So that's another sort of strategic hint when you're trying to do these kinds of proofs, is don't be too quick to simplify, or if you do simplify, don't be too laser focused on the simplified version of your expression, because you might find the insight that you need by looking at what you had before you simplified. So the 10k squared and the 3k and the 3, we have an estimate for. Right? According to my inductive hypothesis, that's greater than or equal to 60k plus 20. So this whole sum, therefore, must be greater than or equal to 60k plus 20, replacing these three terms highlighted in yellow, plus the remaining terms, 20k plus 10 plus 3. Right? So there's the key insight. This orange step here is the key step, because not only has this gotten us closer to the conclusion that we're trying to draw, it also has explicitly made use of the inductive hypothesis, right? Which is the key to knowing that you have truly written a proof by induction. You have to specifically say, here's where the inductive hypothesis is doing the work. And again, because that's the hard part, the rest of the part is probably just algebra, but let's see what happens if I simplify what I have here. If I collect all the like terms, I'll get a 33 from my 20 plus 10 plus 3, and then I still have a 20k sitting out here. And again, I've sort of slowed this down and not tried to combine the 60k and the 20k too quickly. And that's because, looking at my goal is to show why this is greater than or equal to 60k plus 80. So I want this 60k term to stick around. That's why I decided not to combine it with the 20k. Right? Again, you know, simplifying is always a good thing in algebra, except when it can obscure a key insight, like this one. If I leave that unsimplified, then I can focus on the piece that's not 60k, right? Which on our expression here is 33 plus 20k, and on the expression we're trying to get to is 80. So I've now reduced my whole argument down to the question of whether or not we can guarantee that 33 plus 20k is greater than or equal to 80. If we can guarantee that 33 plus 20k is greater than or equal to 80, then we have established this inequality. And so I pull that off to the side. Instead of writing on my napkin, maybe I'm writing directly on my tabletop or something. Is 33 plus 20k greater than or equal to 80 when k is greater than or equal to 6? So this is also a good opportunity to remind ourselves that k doesn't get to be just any old natural number. It has to at least be one of the natural numbers which satisfies my original quantification for n. Right? So we know k has to be greater than or equal to 6 for sure. So what do we know about 33 plus 20k? Well, since k is greater than or equal to 6, 20 times k is greater than or equal to 20 times 6, because 20 is positive, and I can multiply both sides of this inequality by a positive number without reversing the sense of the inequality. So 20k is greater than or equal to 20 times 6, which is 120. And so 33 plus 20k is greater than or equal to 33 plus 120, which is 153. And since 153 is greater than or equal to 80, we know that we have a viable argument here. Right? So one of the things that's interesting to me about this, just to editorialize here before we finish the argument, is that we actually have quite a bit of room here between 153 and 80. Right? K didn't have to be as big as 6 in order to make this work. Right? We might notice that k equals 5 will also make this work. We get 133. K equals 4 would also make it work. It would be 113. K equals 3 would even make it work. That would be 93. It's not until we get to k equals 2 that we get 73, and we would be less than 80. Right? So it would look like this argument would still follow through even if k were greater than or equal to only 3 and not 6. Right? So we have a little bit more room here. And as a mathematician whose goal as a author of proof and as a manipulator of theory, our role, remember, is always to try to weaken assumptions or strengthen conclusions. That is 100% of what theoretical mathematics is. And so this looks like an opportunity to weaken an assumption. And we might say, well, did we really need this to be 6? Or could we have proven this statement for n greater than or equal to 3? So let's put that in the parking lot for a moment and just kind of think about maybe we can prove a stronger statement by letting this n be greater than or equal to 3 instead of greater than or equal to 6. But since we're still dealing with the 6th case, let's just proceed with what we have. 60k plus 33 plus 20k is greater than or equal to 60k plus 153 because k was assumed to be greater than or equal to 6. And since 153 is greater than or equal to 80, the rest of the argument follows through. So again, because of the way I've arranged my scratch paper, I've arranged it so that it already looks like a proof of an inequality going from left to right. So the left-hand side of my inequality equals, greater than or equals, equals, greater than or equals, greater than or equals, equals. And remember, the rule for inequalities is that a left to right working of an inequality is fine as long as all of its inequalities are going in the same direction. Right? As soon as I have a greater than or equal to, all the rest of my inequalities need to either be equals or greater than or equals. If I have a less than or equals at some point after that, then we've completely lost the thread, and we don't know how the original quantity compares with anything. But when you're working from left to right on an inequality, as long as they're all pointing the same direction at every step, then we have a valid line of argument. Right? And so we've proven that this original left-hand side is greater than or equal to the intended original right-hand side. Let's check the base case for n equals 6. When n equals 6, the left-hand side, 10 times 6 squared plus 3 times 6 plus 3. We can evaluate that using a calculator or whatever. Right-hand side, 60 times 6 plus 20, 381, and 380. And since 381 is greater than or equal to 380, we've established the base case. So this might be a good place to pause now that we have all the elements of an inductive proof for this statement and ask, could we perhaps weaken this hypothesis? Do we think this could still be true for n greater than or equal to 5 or 4 or 3? This is a great example of why the base case is so important, because our inductive side of the argument still works for k equals 5. It still works for k equals 4. It still works for k equals 3. But if we try 3, 4, or 5 in our base case, look at how little room we had in between the left-hand side and the right-hand side for the n equals 6 case. If we substitute 6 out for 5, let's just sort of see if it still works. So 10 times 5 squared plus 3 times 5 plus 3. 5 squared is 25 times 10 is 250 plus 15 would be 265, so this is 268. But then 60 times 5 plus 20, that's 320. And so the n equals 5 case does not work. So this is a good sort of test example of why both of these parts of the argument in an induction proof are somehow logically equivalent from one another. Just because the inductive argument that we made over here works for certain values of k does not guarantee that those values of k will satisfy the base case. So it's a bit like saying, if the third, fourth, and fifth dominoes were to fall, they would knock over the next domino in the line. But we can't push over the third domino because that statement's not true. We can't push over the fourth domino or the fifth domino because those statements aren't true. So those aren't even dominoes. Those are just sort of glued to the table. Right? They can't fall. They're not true statements. And the first domino that we can push over is the n equals 6 domino. Even though if the third one fell, it would knock down the fourth one, and therefore the fifth and the sixth and so forth. We can't knock down the third one, or the fourth one, or the fifth one. So, again, illustration of two things. The logical independence of the base case and the inductive case. They both need to work independently of one another. And secondly, that, this is a good example of a place in a proof where there may have been an opportunity to discover new mathematics, right? By weakening the assumptions or by strengthening the conclusions. And in this case, we were trying to see if we could weaken this assumption that n is greater than or equal to 6. And it looked promising, but then it collapsed when we tried to test it on the base case. So now we move from the realm of calculus and analysis into the realm of discrete math and number theory. So we're going to use induction to prove a claim about divisibility of natural numbers. And here the claim is that for every natural number n, so we're going to take that to mean n starting at 1, 2, 3, so forth, that n cubed minus n is a multiple of 6. I want to pause actually before we do this proof by induction to note that there may be another way to prove this statement. Does anybody see what sort of non-induction argument that we might be able to make to show that 6 is a factor of n cubed minus n? n cubed minus n is a product of three consecutive integers. So let me ask this. Do we know for sure that one of those consecutive integers is going to be even? And if we know, then why? So this would be a great thing to prove just using a direct proof, right? That among three consecutive integers, at least one of them has to be a multiple of 2, right? You may even be able to prove this by contradiction. Let's suppose that none of these are multiples of 2 and then arrive at some absurdity, right? But the usual pattern that from the very first time we learn what even numbers are, the pattern is that consecutive integers have opposite parities, right? So if n is even, then n plus 1 is odd. If n is odd, then n plus 1 is even, right? And so from among three numbers, three consecutive integers, either one of them is even if it's the one in the middle, or two of them are even if they're the first one and the third one, right? So at least one of these factors has to be even. And so we know that this quantity is divisible by 2. What can I say about whether this quantity is divisible by 3? We have to conclude that yes, one of these factors will also be a multiple of 3 just because of a proof by cases, right? When we divide by 3, either we're going to get a remainder of 0 if we are a multiple of 3, or we're going to get a remainder of 1, or we're going to get a remainder of 2. But from among three consecutive integers, each one of those three cases is going to be represented, right? One of these factors is going to have a remainder of 1 when you divide it by 3, and so is not going to be a multiple of 3. One of the other factors is going to have a remainder of 2 when divided by 3, so it will not be a multiple of 3. But the third factor will have a remainder of 0 when divided by 3, and so will be a multiple of 3. We can't have three consecutive integers unless one of them, and in fact exactly one of them, is a multiple of 3. So we know now that from among these three factors, there's definitely going to be one which is a multiple of 2, and there's also going to be one which is a multiple of 3. So what do we get to conclude as a result? Right. Because 6 is a product of 2 primes, 2 times 3, right? We can't have this expression divisible by both 2 and 3 unless it is divisible by 2 times 3, namely 6. Right? 2 and 3 have no common factors. They're relatively prime to one another. And so if a number is divisible by by each one, then it's divisible by the product. Right? In fact, it ends up being if and only if. So yeah, there is the non-inductive proof of this statement, right? Just by writing this out, we can say one of these factors will be a multiple of 2, one of these factors will be a multiple of 3, and therefore this whole expression necessarily will be a multiple of 6. Right? Done, QED, check mark. Right? But that's not where we're driving at today, right? We want to be able to also write up a proof of this that uses induction. So let's do that as well. Again, starting with the inductive step. And at the inductive step, we're going to take our assumption that 6 is a factor of k cubed minus k. So that the statement is true for n replaced by an arbitrary k. And then we need to try to deduce that 6 is a factor in k plus 1 cubed minus k plus 1. One of the places to get screwed up on this is to forget parentheses around your k plus 1 when you're writing this expression. Try not to forget that because that's the source of a lot of people's sort of algebraic angst. You're trying to do the work, you can't get the two ends to match up, and it's because you just forgot to put parentheses around your k plus 1s. Okay, so let's try and work from the initial inductive assumption and try to get closer to our inductive step conclusion. And here's a place where we just have to plug in the definition of divisibility. K cubed minus k is divisible by 6 means that there exists an integer, I'll call it a, such that k cubed minus k is equal to 6 times a. Right. That step is probably the most crucial step in this proof, is just understanding how to implement that definition. You're going to wind up with a lot of proofs, especially in areas of discrete math like number theory, abstract algebra, combinatorics, where by the time you unravel the definitions in what you're trying to prove, the proof will be 90% done. Then it's just a matter of trying to join up the two ends. So we're going to do the same thing with our conclusion that we're trying to make. K plus 1 cubed minus k plus 1, if we want to show that that's a multiple of 6, then we need to show that there exists an integer, which we should give a different name here, call it b, such that k plus 1 cubed minus quantity k plus 1 is equal to 6 times b. And so the real question for us now is, what's b? If I know for sure that k cubed minus k is 6 times an integer, how do I show that as a result k plus 1 cubed minus k plus 1 is 6 times some potentially other integer? So if we can find this b, then we're going to be done. And probably the b that we find here is going to be constructed out of quantities that we already know from our inductive hypothesis. Namely, it's going to be constructed out of a's and possibly k's. So to figure out what it should be, as usual, we just have to figure out how to plug in our inductive assumption into the thing we're trying to prove. We need to discover k cubed minus k from within this expression that we don't know anything about yet. So we'll expand out k plus 1, the quantity, to the third power. Bring out our old friend, the binomial theorem. It's k cubed plus 3k squared plus 3k plus 1. Then I'll distribute the minus sign across the k plus 1 over here to get minus k minus 1. And again, I'm pausing here and not simplifying because I want an opportunity to see if I can already identify the terms that we're trying to identify. And sure enough, here's a k cubed, and there's a minus k. And if I had simplified, I might have lost that insight. So the k cubed and the minus k, we can use our inductive hypothesis to replace by 6a, where a is some integer. So I have 6a plus 3k squared plus 3k. We're trying to show that this quantity is a multiple of 6. And so I'm not worried about this first term. This first term is 6 times an integer, so I already know that that first term is a multiple of 6. So that's not going to be the problem child here. The problem child is going to be 3k squared plus 3k. I can look at that and say, well, it's definitely a multiple of 3 because both of these terms have a factor of 3 just sitting right there. It's already been exposed. So that's not enough, though. We need to show that it's a multiple of 6, not a multiple of 3. So we have to work a little harder. And this is where having done this work might sort of prime us to figuring out what to do next. Let's try and factor 3k squared plus 3k. That's 3k times k plus 1. Right? And there is a point at which we, again, can make this argument about consecutive integers. K times k plus 1 is the product of 2 consecutive integers. If we were feeling particularly verbose, we could break this out into a proof by cases. Case 1, let's assume that k is even. Well, if k is even, then it's equal to 2 times an integer, and then this term will be equal to 3 times 2 times some integer times k plus 1. But that 3 and that 2 could come together to give me a 6. And we're done. The second case is if k is odd. Well, if k is odd, then k plus 1 is even. And if k plus 1 is even, then k plus 1 is equal to 2 times an integer. And I can get that 2 and this 3 together to make a factor of 6, showing that this term is indeed a multiple of 6. So we're going to just, for the sake of brevity, we're going to not break out those cases and write them out in all their gruesome detail. We're going to trust that you can do that if you want to, writing that proof by cases. This product has got to be even because it's a product of 2 consecutive integers, and one of those integers necessarily must be an even number. So k times k plus 1 is equal to 2 times some integer, which we're going to call c. So there exists a c, which is an integer, such that k plus 1 is equal to 2c. And since k plus 1 is equal to 2c, we can simplify this expression into 6a plus 3 times 2c, and then this 3 and this 2 come together to make a 6, and we can factor that 6 out to get 6 times a plus c. And so this is a place where it almost feels, I know sometimes reading a proof like this you can feel a little bit unsatisfied, because our goal was to discover an integer b. And so what we like to do is we like to be able to say, oh, b is equal to 15, or something concrete here. But instead, we discover that b is equal to a plus c, where a was some mysterious integer that was given to us by the definition of divisibility and from our taking of the inductive hypothesis. And c was another mysterious integer that was given to us by the definition of divisibility by 2, which we got from making the observation that this product of 2 consecutive integers must be even, that we obtained out of simplifying the left-hand side of the thing we're trying to prove in our inductive step. And so it's not super satisfying, but sometimes that's just how these things go, right? We don't know really much of anything about what kind of integer b is. We just know that it is an integer because it's equal to an integer a added to an integer c, and we know that anytime I have 2 integers and I add them together, the result, the sum, is again going to be an integer. So b is an integer because a and c are integers, and therefore so is a plus c. So it's not, again, the most, what a mathematician calls constructive. It's not constructive. It doesn't tell me how to find this b. It just shows me that this b exists, predicated on the fact that a and c existed, and we just added them together to get our b. And so reading this from left to right, k plus 1 cubed minus the quantity k plus 1 is equal to 6 times some integer. Therefore, 6 divides into k plus 1 cubed minus k plus 1, which is what we're trying to prove in the inductive step. Let's finish with the base case. When n is equal to 1, we just need to show that 6 divides into 1 cubed minus 1. But 1 cubed minus 1 is equal to 0. Is it true that 6 divides into 0? Sure, because 0 is equal to 6 times an integer. Namely, 0 is equal to 6 times the integer 0. 0 is that funny integer which is a multiple of every other integer. There is no other integer that satisfies that description. And therefore we're done. So the base case, relatively simple. The inductive step just required us to, again, most important step was just being able to plug in that definition of divisibility to get us from our original statement about factors and divisors into an algebraic reality that gives us this mysterious integer a that we can then do some algebra with. And after we do all the algebra, we show that indeed k plus 1 cubed minus k plus 1 must also be a multiple of 6, because it's equal to 6 times the quantity a plus c, where a was this integer and c was the integer we got from this observation. So let's write this up into a formal proof. So we're going to prove this again. We'll tell the reader of the proof that we're going to start with, we're going to frame this whole thing around a proof by induction. So we proceed, spelling proceed correctly, by induction on n. Anytime you can leave the reader those little breadcrumbs that sort of tell them here's the overall strategy that we're going to use in the proof, that is so immensely helpful to the person reading it, so that they know the overall structure, they know what the entire building looks like, so that when you're looking at individual screws and boards and nails, they can put that into a larger context. So we proceed by induction on n. We'll start with our base case. In our base case, from the scratch work over here, this was the case where n was equal to 1. When n equals 1, we wish to show that 6 is a divisor of 1 squared minus 1. Okay, how do we show that? We just show that by observing that 1 squared minus 1 is equal to 0, which is equal to 6 times 0. Our goal, after all, was to show that 1 squared minus 1 was a multiple of 6, which we do by showing it's equal to 6 times an integer. Since 0 is an integer, this demonstrates that 6 is a factor of 1 cubed, minus 1. And I've got to fix that typo. This is a cube, not a square. There we go. So we've proven the base case, and we can move on to the inductive case. We make the inductive hypothesis. Assume that for an arbitrary k in the natural numbers, we have 6 is a divisor of k cubed minus k. We wish to show that 6 is a divisor of k plus 1 cubed minus k plus 1. And by the way, a lot of times when you read, what should I call them, more veteran mathematicians write proofs like this, they won't always be this explicit in writing out, here's the inductive hypothesis, and also here's what we're going to try to prove. But again, for you all, it's a good practice to get into, and you can always fill in those gaps if you're reading someone else's proof and they haven't written out exactly what it is they're trying to prove along the way. So now we've made our inductive hypothesis, and we've told the reader, here is the statement that we now are going to try to justify. And so now I'm going to try to go from this step on my napkin down to this step. In other words, just plug in the definition of divisibility by 6 to get us from our assumption down into the algebraic statement that we can make about k cubed minus k. So we'll say, by definition of divisibility, there exists an integer. And again, it's always good practice. Before you use the name of a new variable in any sort of equation or expression or anything, you have to tell the reader where it comes from. And this a is coming from the definition of divisibility. There exists an integer a such that k cubed minus k is equal to 6a. Scroll that down a little bit here. So by definition of divisibility, there exists an integer a such that k squared minus k is equal to 6a. And now we're going to rejoin the napkin, okay, at the left-hand side of the equation that we're trying to justify. In other words, we need to show that 6 is a factor of k plus 1 cubed minus k plus 1. So we're going to start from that k plus 1 cubed minus k plus 1. K plus 1 cubed minus quantity k plus 1. We do all of the expansion on the left-hand side that we did right here to get k cubed plus 3k squared plus 3k plus 1 minus k minus 1. So there's that whole mess. And then we do the crucial step, which is apply the inductive hypothesis. We notice that there is a k cubed minus k. We could even bring that out in parentheses if we like to. K cubed minus k. This might make it read a little bit nicer, because then we can see what's left over. Plus 3k squared plus 3k. Whoops. Get that lined up correctly here. Right? So doing that is, again, this is sort of a help to the reader. It sort of puts the focus in on that quantity in parentheses, k cubed minus k. Because now the reader should be able to tell, oh, I know why that quantity is important, because we made an inductive hypothesis about that quantity, that this is equal to 6a plus 3k squared plus 3k, and this is a good place to remind the reader, by our inductive hypothesis. I have to abbreviate that because my screen isn't going to be wide enough. There we go. So by the inductive hypothesis, k cubed minus k was equal to 6a. And so we're already down to here, 6a plus 3 times k, k plus 1. Let's do that factorization, plus 1. And I think probably what I would do if I were writing up this proof in prose, which I guess we're doing right now, is I would break out of my equation mode, because we're going to have to say some words about k times k plus 1. Right? So I'm going to go down to a new paragraph and say, since k plus 1 is a product of two consecutive integers, it must, in particular, be an even number. Whether or not that requires proof in this context is, again, context dependent, right? I think probably this is the kind of statement that you proved before I joined your class, back when you were working first on direct proofs, right? So let's not worry about needing to reprove this, but maybe we could say by previous results or something, right? So we'll just move on from there. Since k plus 1 is a product of two consecutive integers, it must in particular be an even number. Thus, again, by definition of divisibility, in this case divisibility by 2, there exists an integer. So introduce the integer first, and then say what it satisfies, such that k times k plus 1 is equal to 2 times c. So by definition of divisibility by 2, we get the integer c for which k times k plus 1 equals 2c. This implies that, and then we go back to our calculation that we were doing from before, right? Where I have this k times k plus 1, we'll substitute that back in. So remind the reader of where we left off. So we're going to rejoin our previous calculation already in progress. K plus 1 cubed minus quantity k plus 1 is equal to 6a plus 3 times k plus 1. And then now that's going to be equal to 6a plus 3 times 2c. And that's equal to 6 times the quantity a plus c. So we bring the reader back into this calculation and show that it gives us 6 times quantity a plus c. And now we're almost to the end of our argument here. We just need to do this last little step and remind the reader of why a plus c is an important quantity. Even though we don't know anything about the specific numbers, we know what kinds of numbers they are. We know that a is an integer because of what we said up here. When we first introduced a, it came from the definition of divisibility, and therefore it was an integer. Also, we know c is an integer because it too came from the definition of divisibility, in this case divisibility by 2. So since a and c are integers, and the sum of any two integers is again an integer, that means a plus c is an integer. So this is the place to make that connection for the reader. Since a and c are integers by assumption, and the sum of any two integers is again an integer, which is also a statement that kind of requires some proof, but that proof is outside the scope of our course. That's the kind of question you sweat in abstract algebra quite a bit. But we can conclude that a plus c is an integer, and I'm going to call the a plus c, I'm going to call it b, just to kind of get us back onto our napkin over here. B equals a plus c. What do we conclude about it? We conclude that it's an integer as well. And k plus 1 cubed minus k plus 1 is equal to 6b. There's the key insight. Right? Because now, one last time, we plug that definition of divisibility back in. We've shown k plus 1 cubed minus k plus 1 is equal to 6 times an integer. And therefore, by definition of divisibility by 6, we conclude that 6 is a factor of k plus 1 cubed minus k plus 1, as desired. So by the principle of mathematical induction. This is like the copy pasta at the end here. We have shown 6 is a factor of n cubed minus n for all natural numbers, n. Put in my little square end of proof box that we have to earn through much wailing and gnashing of teeth, and there it is.